we start, let's take a look at my simulation. This is the simulation of the must-part homework. It's simulating 3 balls with different mass, initial velocity and initial position tied with springs with 3 different spring constants. There is total energies versus time graph on the right and averaged energies over time versus time graph on the left. The blue and red curve represent kinetic energy and potential energy respectively. In the second simulation, we have 2 balls tied with 1 spring and we simulate the motion of 2 balls. This is the period of the oscillation, which is around 0.88 on average. In addition, I plotted 3 graphs to check my simulation results. There are position versus time graph, velocity versus time graph and acceleration versus time graph respectively. The blue curve represents the motion of the left-hand side ball, which is the lighter and smaller ball, and the red curve represents the motion of the right-hand side ball, which is larger and heavier. As you can see, the period is 0.896 seconds. As you can see, most parts of my code are just like the previous one, which I have already explained in the previous video. The only thing new is the use of lists. In order to reduce the length of my code, I named a list K instead of naming K1, K2, K3. In the list K, I have put 3 elements into the lists, which is 3 different spring constants in this case. The list V and list D do the same jobs. In the main part, I generate a list named balls, which is empty right now. In the first line of for loop, we have to declare the range, which is 3 in this case. Instead of counting from 1, the list start counting from 0. The first item in the list is named 0th term and the second item is named first term, so forth and so on. In the for loop, we generate ball and declare its initial position, initial velocity and size. We then append the ball into the list named balls and the for loop will run for 3 times. 3 different balls will be generated after the for loop done running. The list named springs does the same. As usual, we have to declare some variables we might be using later before entering the while loop. The count I declared in this case is to count how many times the for loops has run through. The total K is to sum up all of the kinetic energies over time, and so do the total PE sums up all of the potential energies over time. In the third and fourth line of while loop, I generate 2 lists which named K and P respectively. These 2 lists are to help me store only 3 values and it will refresh every 3 times the following for loop runs. In first few lines of for loop, we declare all of the functions of balls on springs motion. The new thing over here is the spring axis and the norm function. The spring axis is the direction where the spring moves. In the previous list spring, we have fixed one end of the spring and we expect that the spring will move with the ball. What we do is ball's position minus the fixed position of spring. This is how we get the spring moves. The norm function is to get the vector of spring axis. In the following code, the kinetic energies will be appended into the KE list every time, so does the potential energies. The total KE sums up all of the kinetic energies generated over time and the total PE sums up all of the potential energies generated over time. The count over here, it will add up 1/3 every time the for loop runs. This is because only one ball's motion get updated every single time the for loop runs. We have to run the for loop for 3 times to get every ball's motion updated. In the next 2 for loops, we sum up the every 3 items in the list, which are kinetic energies and potential energies of 3 balls of the same moment. The C and D calculate the averaged energies over time. In the last part of our code, we have our graph plotted. In the optional part of my assignment, I have generated 2 balls with different sizes and masses. They are tied with 1 spring with the original length of 0.5 meter and spring constants of 15. In the main while loop, I use the change spring position vector to determine motion state of the smaller ball, which is on the left-hand side, as P smaller than 0, which means the position vector changes from 1 to -1. The count will add on 1. As the time increases, the period of the oscillation will be T over count, which is the average. In addition, I plotted 3 graphs to help me determine whether my simulation is right. We have position versus time graph, velocity versus time graph and acceleration versus time graph. The blue curve represents the motion of the smaller and lighter ball on the left side, the red curve represents the motion of the bigger and heavier ball on the right side. Take a look at the time graph. The period of the oscillation will be peak to peak, and it's almost the same as our previous simulation.